Hello everybody, my name is Alexey Fedorenko. I am from Skolkovo Institute of Science and Technology, located in Moscow. And in this presentation, the practical point of view to the lattice structures will be provided. So I show two cases for different industries. The lattice structures were proposed rather for a long time ago, as you can find in some references below on the slide. The main concept is to use lattice of different shape as a core for sandwich panels. And examples of such panels you can see on the right side of the slide. Here it is pyramidal type and braided type core. For the strength analysis and analytical prediction of buckling load of the lattices were provided. And in addition, from mechanical testing, it was observed that there is debonding between outer shells and the core due to a poor solder joint properties. It is possible to produce lattice from fiber-reinforced composites. The examples of anisogrid lattices are used for the structures where no need in skin, as shown for fairing of space rocket and for the drone structure. It is also possible to manufacture composite panels, as shown on the slide. Thermoplastic composites are useful for this purpose since they allows forming process. However, according to the reports, failure modes associated with buckling and failure in zones between the lattice and the skin frequently occurs. The lattice structures are very promising due to high mechanical characteristics, but in the same time they are still not very widely used in industry due to problematic manufacturing, control of defects, and difficulties for the computational analysis. Our motivation that thanks to the modern manufacturing technologies such as laser cutting and welding, high precision stamping, it is easy to produce such structures, and in support of robotics, non-destructive inspection, it is possible to control defect. And the final point is that high performance computing allows the analysis of such lattices on the level of every reinforcement rib, every reinforcement bar. Trying to find an optimal core structure, we directly use a topology optimization procedure. Elastic compliance is an objective function which is supposed to be minimized. The initial topology is rectangular plate, and two load cases are considered for the analysis. The target mass is 10% in comparison with initial plate mass, and outer surfaces are frozen, so no optimization in this region. And the result of optimization is shown on the slide, which is quite a complex shape, consists of a lot of truss-like elements between outer shells, and we can simplify the obtained topology by the pyramidal-like core, which is feasible for manufacturing. This is the first concept for the construction industry. The idea to fill the space between outer sheets of our sandwich with the concrete, so it allows to refuse the traditional metallic bar reinforcement and to skip a long process of the frame construction. For the evaluation of proposed structure, we compare it with a traditional concrete plate reinforced by metallic bars. We simulate the response to the bending load, and the scheme of finite element model is presented on the slide. We use a special modeling technique of Abacus software, which called embedded element, and it allows to use beam elements for bars into the solid elements for the concrete media representation. So Drucker-Prager plasticity model is used for model, and in addition a failure criterion is applied, so the structure is loaded up to failure. For the metallic components we use classic plasticity, and Drucker-Prager plasticity is used for concrete. It allows to consider the differences of yield strengths for the tension and compression, and Kolmogorov failure criterion was chosen to consider equivalent plastic strain accumulation. For the proposed plate, we use the identical modeling approach. On this slide, the one with stress distribution in the metallic component is presented. We use classic isotropic plasticity for the metal components, and concrete is removed from the screen. And as you can see, yielding occurred in the middle of the bottom skin. Comparing force versus deflection diagrams for the two plates of the same external dimensions, we can conclude that for the identical volume ratio of metal, the proposed structure has nearly 2 times higher ultimate stress in comparison with the conventional plate. If we would like to achieve the same ultimate stress, we need to a volume fracture of 2 times less for the proposed plate in comparison with conventional one. In construction, typically a fixed assortment of the plates is available, and this is a demonstration where we need the plate of extra length. So the proposed structure looks very effective due to the enhanced stiffness. In the second case I want to present, this is a proposed structure of pressure bulkhead. This is the rear part of the fuselage. As previously, it consists of two skins and the lattice between them, as shown on the slide. The diameter of pressure bulkhead is 3 meters, and the characteristic length of this rib between shells is 90 millimeters. So the one of the most important critical requirements is damage tolerance. The statement is it should sustain 0.65 bar pressure with the crack length from 800 to 1000 millimeters, and aluminum material is assumed. The finite element model was developed for the analysis of pressure bulkhead using shell elements, and again we compare classical structure and the proposed one with the same masses. And fixed nodes for boundary conditions are highlighted on the slide, and the pressure applied in the internal surface. On this slide, there is a comparison of maximum von Mises stress through the thickness for both structures, assuming no crack presence. And for both structures, maximum stress is below the yield limits. However, for the proposed structure, there is no benefits since there are a lot of stress concentrators between the ribs and the internal and outer skins. And this is the same analysis, but with the assumption of crack presence of 1 meter length on the skin. For the modeling of the crack, we simply use disconnection between mesh nodes, and as you can see now, the crack causes much higher stress values for conventional structure. Abacus software allows to compute J integral for the contour over crack tip, and using J integral we can calculate stress intensity factor. Here we assume that the first mode is prevail. So we compute it for two crack tips, and in the plot we calculate the ratio of stress intensity factor to the critical one for the all crack tips, depending on the level of pressure load. And it can be concluded that since we have a structure of identical mass, the damage tolerance is increased in proposed structure about 2 times. And the conclusion is that lattice structure core is close to the optimal one, as we verify using a simple topology optimization analysis problem. And from literature review, we can conclude that many concepts were proposed, but not so much implemented for today. However, modern technologies allows to solve many problems revealed in early studies. Here I mean not only development of manufacturing technologies, but in our presentation we show that for today it is possible to develop heavy finite element models to consider different components such as concrete in our cases, and to conduct the detailed analysis of entire lattice.